Hello guys, and in this video we're going to talk about the logistic regression. So first of all, the essence of the logistic regression is using a multiple one or multiple predictor variable to predict binary response variable. And basically the model we are using is log of pi over 1 minus pi equal to e to beta 0 plus beta 1 x1 plus beta 2 x2 beta 3 x3, keep going, right? So that's the most important thing we're going to learn in this section. So let's get to the details. First of all, so we typically dealing with binary response variable, right? Meaning binary meaning if you look at whether or not a person smokes, it's either non-smoker or smoker. For the success of medical treatment, either survive, let's say, cancer treatment, survives the cancer or dies from the cancer. So those are the what we call binary output, right? In basic statistics, you also learn like success or failure, right? This is more general, like broader term to understand the binary outcomes. In the computer system, it's like 0, 1, right? 1, 0. This is a computer system. These are all binary response, could be binary response variable. So basically we use one or multiple predictors variable to understand, to predict the binary response variable, as we talked about in the previous slide. So for example, let's say we want to use the height to predict the gender, right? That's the task. So here y represents gender, 0 is male, 1 is female. And then here the predictor variable x is the height in inches, right? Now basically come up with this ordinary, first of all, we try the ordinary linear regression, and this is the code, right? Reg model, regular model equal to LM represent linear model, and then gender is predicted by the height. Data we use in pause data. And here's we get a summary output of the regular model. And this is basically our summary output. And then based on the linear regression model, we know that we're going to run the model as predicted gender equal to beta 0. This is beta 0. This is beta 1. Beta 0, which is 7.343647 plus negative 0.100658 times height. HGT represent height. So this is the model. If you're using a linear regression model, and then you can see that this is the original plot. All the circles are here. All the circles are the original plot. So your outcome either could be male based on different height, or female based on different height. So definitely, if you look at the graph, this linear regression model is not effective, right? Because it doesn't capture the special feature of the graph. It's not effective in this case. So basically it fails, right? Linear regression model fails to capture the nuances of this particular data set. So that's why logistic regression is being utilized, right? So ordinary linear regression is used a lot. And basically it's taught in every intro to stats course, but the logistic regression is rarely taught, even mentioned in the basic statistics course because of due to the calculation complexity. But now, once we understand the R, then we have enough computing powers to implement logistic regression using R. Okay. So now let's take a look at how we define some of the important elements in this logistic regression. Start with the pi. Pi basically here is what we call the proportion success, right? Pi represents proportion success, or you can say probability of success. So in ordinary regression, the model predicts the average y value for any combination of predictors. And here the response variable will be 0 and 1, right? 0 means male, 1 means female from the previous example. So here, average of y value equal to total y value over the sample size. So number of females, sample over the sample size. Right? This is what we call the proportion success. So the goal of the logistic regression is to predict the true proportion of success pi at any value of the predictor variable. Or you can say predict true probability of success pi at any value of the predictor. So the binary logistic regression model start to define the binary response variable y, and x is the quantitative predictor variable. And the pi here is a proportion of ones. You can say yes or success, right? More general terms, it's kind of like success at any x values. And then equivalent form of this logistic regression model is, this is a logit form, right? Log means the same thing as ln, meaning natural logarithmic function. And then pi is probability success over 1 minus pi is probability failure. And this is what they call the odds ratio, right? Equal to beta 0 plus beta 1x. And then we're going to turn this into the probability form, right? I'm going to show you how to do the conversion, but first of all, keep in mind this log is same thing as ln. Log is equivalent to ln. Ln is log with base e. So now I'm going to show you how to do the conversion from the this logistic form to the probability form. Okay. So now let's look at this. So basically we have a logistic regression model here with one predictor variable, right? It's only one predictor. So this is beta ln with log with base e and then pi over 1 minus pi. And this is equal to beta 0 plus beta 1 times x. Now we're going from this logarithm function to the exponential function. We're going to using this base e to that power, right? So pi over 1 minus pi equal to e to this power, right? Just like remember back in the exponential function, let's say this ey equal to x, then you're going to do e to the x equal to, so y equal to e to the x. So here the y value equal to e, the base for the logarithm function to the x. And similarly here, pi over 1 minus pi equal to e to the beta 0 plus beta 1 times h. So now from here we can solve for pi, right? So make it a proportion here. So pi over pi equal to e beta 0 plus beta 1 times x. The key thing here is solve the pi. So we do cross multiplication. Pi times 1 and then 1 minus pi times e to the beta 0 plus beta 1 x. Now we can simplify that. Pi equal to distribute, we get e beta 0 plus beta 1 x minus pi times e beta 0 plus beta 1 x. And now from here, I'm going to add both sides of the equation by pi times e to beta 0 plus beta 1 x. Same thing on the right. On the left hand side, pi times e to beta 0 plus beta 1 x. From there, we're going to cancel this common factor. Opposite terms here, we get pi plus pi times e to the beta 0 plus beta 1 times x. So this is e to the beta 0 plus beta 1 times x. Now from here, we're going to solve for pi. So factor out of pi, we get 1 plus e to beta 0 plus beta 1 x. And on the right is e beta 0 plus beta 1 x. Now we're going to divide by this common factor on both sides of the equation, 1 plus e beta 0 plus beta 1 x. On the right hand side, simply 1 plus e beta 0 plus beta 1 x. So basically, we end up with the pi by itself, right? That's pi is the main focus. Pi means probability of success, a proportion of success. So it's e beta 0 plus beta 1 x over 1 plus e beta 0 plus beta 1 x. So this is what you see from the PowerPoint slide. So let's go back. That's how you do the conversion. Let's go back to the PowerPoint here. So that's why we end up with this. From the logistic regression model to the probability form, right? I just show you the conversion step by step. Yeah. And this is one of the most important things to understand the logistic regression model, right? Because eventually we're going to focus on the pi. Pi is the main focus. Pi is probability or proportional success. And typically, if you plot this logistic regression model, you're going to see something like this. This is the graph of it. And basically, for any given x values, we get a corresponding probabilities here. Y value is a probability. Probability go from 0 all the way to 1, right? This is 1. And with any x value here, you're going to have a different probability values. So that's why the logistic regression is like this. And on both tails, right, the probability on the left tail, probability approaches 0. On the right tail, the probability approaches 1. So basically, if you run the logistic regression using R, so this is the code how we do that. So we do logit model equal to generalized linear model, GLS generalized linear model. And we're using height to predict gender. And here is what we call the binomial model, right? So logarithmic function is also kind of like a binomial model, so that's why it's binomial here. And And then we can gather the post data set. And then we get summary of the logistic model. So this is kind of like the summary of what we have here. So if you want to write this logistic regression model, you'll be like this, right? Predicted y values or predicted gender. So yeah, let me just quickly erase this. Let's feed in the proper model here. So the log of pi over 1 minus pi equal to e beta 0 here. This is beta 0, beta 1 is x1, and will be e to the beta 0 plus beta 1. So it will be 64.1416 minus 0.9424 times the height, FGT. So that's basically the logistic regression model. And then basically here we can solve for pi, right? So the pi will be based on the earlier calculation to show you it will be e to the 64.1416 minus 0.9424 times height over 1 plus e to 64.1416 minus 0.9424 times height. So here you put in any given height for the participant, right, or for the object here, and we get a corresponding probability, right, of being female. So that's how we basically use the model to make prediction about the gender. And basically, so this is the logistic I just showed you earlier, logistic regression model, and from that model, we come out. We start with the logistic regression model log pi over minus pi here makes e to 64.14. We just take 2 decimal place for that, but we're going to keep the whole thing 0.9424 times height gt. And then we basically convert it and get a pi equal to that. So pi here represents proportion of probability of females at a certain height. Let's say if HGT equal to 60 feet, right? So basically we can replace x with the 60 and then get the probability or proportion of the female for the 60 feet tall, right? So here we do height equals 60 feet, 60 inches. So we're talking about inches here. The unit is inches. And then replace this height with the 60. So the pi equal to e to 64.1416 minus 0.9424 times the 60, right? Over 1 plus e 64.1416 minus 0.9424 times 60. And then basically we can get probabilities here, right? I'm going to use Excel to show you the result. Copy this, and then let's go to the Excel. I'm going to paste that really quickly so you can do the calculation underneath it. So we do this. So EXP, first of all, open parentheses, EXP is 64.1416 minus 0.9424 times 60. That will be the numerator, denominator, close out, divide by 1 plus EXP 64.1416 minus 0.9424 times 60. And then close parentheses, and then we're going to come up with this. So probability is 0.999499, right? That's pretty high probability here. That means, you know, if someone's height is 60 inches, which is 5 feet, most likely you'll be a female, right? With a 99.95% of chance you'll be female. So that's how we interpret these probability values. So the answer here is 0.9949. It's 0.9993. 9994, yes. So I'm going to just quickly, so this now, right, it's 0.994. So, and then if you plot the 3D logistic regression model, we're going to see something like this. And then at 60 inches, you see the probability is almost, for calculation is 0.99949. It's almost equal to 1, right? With 100%, 99.95% of chance, if the subject's height is 60 inches, it will be female, right? With a 99.95% chance. And similarly, if let's say someone with a 75 inches height, right? In this case, the probability will be close to 0, right? Meaning you'll be a male. So the chances that this is probably a male. Okay, so that's how we interpret these probability values. And then if that's somewhere of 65 inches or 70 inches, with the 70 inches, then the probability will be somewhere around 18%. If a subject's height is 70 inches, with 18% of chance, it's going to be a female. So you can interpret every single one of the probability value here. And the next example is about golf, right? Golf parts. Okay. So in this case, we have two variables. First one is length, and then second variable is the parts made or missed, right? So we're gonna build a model to predict the proportion of the parts made, which is a success event, right? Missed would be the failure event. Based on the length, right, of the golf ball to the parts. So that's a 3 feet. This is 3 feet from the part, 4 feet from part, 5 feet from part, 6 feet from part, 7 feet from the part. And each one have different probability for sure, right? And so for 3 feet from the part, 84 golf balls made and 17 missed, right? For 4 feet from the part, 88 made, 31 missed. 5 feet from the part, 61 made and 41 missed. So 6 feet from the part, 61 made and 64 missed. 7 feet from the part, 44 made and 98 missed. As you can see, the further the golf ball from the pot, the probability gets smaller, right? Gets less likely. Golf ball, we're gonna have a pot mate, right? So that's basically the general trend here. So here we build a logistic regression model based on length. So there's also code for the generalized linear model. So using made based on the length, using a logistic regression. So that's why family equal binomial data is a part one. So all the codes we will talk about it in our in-person class. And then basically we come up with this logistic regression outputs. So we're gonna do this, right? So we're gonna do log pi over 1 minus pi equal to e. This is beta 0, is that beta 1. So beta 0 is 3.25684 minus 0.56614 times length, right? 3 feet from the pot all the way to 7 feet from the pot. If you look at the probability value here, this is 3 star means it's highly significant. So this is highly significant, meaning length is extremely significant predictor, right? It's highly significant predictor of the part mate, predicted part mate. Okay. So this is the plot, right? So basically, they plot it, you get something like this, and then we try to fit a linear model here. It doesn't look like a good fit, right? Not ideal. But if we fit, so this is the linear part of the logistic fit, and if you fit logistic regression model, as you can see, it's much better fit. Meaning, we can predict the part A with a higher confidence or with a higher accuracy. Better fit. So logistic regression definitely is much better fit to predict the part mate. And then let's take a look at the odds ratio, right? This is one of the most important terms in the logistic regression model. Definition is that we're using pi over 1 minus pi. This is called odds ratio. Also, you can say probability yes or probability no. Or probability success is equivalent to probability success over probability of failure. And that's odds ratio. So the odds ratio equal to pi over 1 minus pi. And then you can also solve for pi, right? Based on the put into the proportion, make the proportion, cross multiplying, and we're going to end up with pi equal to odds ratio over 1 plus odds ratio. So let's take a look at the example of the odds ratio here. So logistic regression model, right, from the basic model with 1 predictor variables. And the logistic regression model assumes a linear relationship between the predictors. Here, only 1 predictor X, and then the log of odds, right? This is pi over 1 minus pi is odds ratio. So it's linear relationship between them. log of odds ratio and then the predictor variable. So the odds here will be pi over 1 minus pi is equal to E raised to beta 0 plus beta 1x. And if let's say we place x with x plus 1, right? Meaning when the x value is increased by 1 unit, going from x to x plus 1, and when x value increased by 1 unit, and the odds ratio will become e to beta 0, right? So odds ratio of the e beta 0 plus beta 1 times x plus 1 over e to the beta 0 plus beta 1x. We do a little bit of exponential operations, and we're going to get this get cancelled, beta 1x get cancelled, right? We end up with the e to the, actually let me do the calculation. So basically it's e beta 0 plus beta 1x plus beta 1. Distribute this, you get minus beta 0 minus beta 1x. I would cancel the common terms here. So this get cancelled. Beta 0 get cancelled. Beta 1x get cancelled. So that's why we end up with e to the beta 1. So as you can see, when x value increased by 1 unit, then odds ratio will become e to beta 1. So let's take a look at the example, right, about in the medical field. So we have a transcranial magnetic stimulation with a placebo, right? TMS for migraines. So they use two different treatments for migraines. First one is transcranial magnetic stimulation. Second one is using placebo. So this is a typical 2x2 contingency table. And the reason why it's 2x2 contingency table because we have a row factor with the binary outcomes, right? This is row factor, and then this is column factor, also binary outcomes, binary factors, right? So TMS of placebo, that's a column factor, 2 outcomes for column factor. For low factor, you get a pain-free, no pain-free, right? That's row factor with the binary outcomes. Now we're going to calculate the odds ratio here. So probability, this means probability of TMS would be 39 over 100, 39 over 100, so 0.39. And the odds ratio will be probability of success over probability of failure. Probability of failure here, so will be 39 over 100 over 61 over 100. 61 over 100 as a probability of failure, meaning no pain free, right? Still as a pain. And if you simplify, so we're going to cancel the 100 here. You get 39 over 61, so that's 0.639. And that's the odds ratio for TMS. Okay. Now let's take a look at the odds ratio for placebo, right? Very similar probability of placebo with no pain, pain-free. That will be 22 over 100. This is calculated over 100. This is 39 over 100. And from there, we can calculate the odds ratio. So we do 22 over 100 by 70 over 100 probability of success over probability of failure. And that turned out to be 0.282, right? This is 0.639. And then the odds ratio of those two treatments is going to be 0.639 over 0.282. And then when you divide them, we get 2.27. And the way how we interpret this is odds are 2.27 times higher of getting relief, pain relief, using TMS than the placebo. That means TMS treatment is much better, right? With a much higher chance to reduce the pain. And that's how we use it, how we generate the odds ratio from the 2x2 contingency table here. If we try to fit a logistic regression model for TMS data, we basically come up with this, the following outcomes, right? So we're going to get log. So based on these outputs, first of all, this highly significant with a 2-star, right? Meaning this predictor is highly significant. So the model we generating pi over 1 minus pi, and it's going to be e to beta 0, beta 1, minus 1.2657 plus 0.8184 times group TMS using TMS treatment. And then here the odds ratio. Okay, I'll quickly just go over this. So this is the model, and the odds ratio will be E beta 1, right? So odds ratio becomes E to the beta 1. From the previous slide, E beta 1 is what we call the odds ratio when X increased by 1 unit. So going from the placebo to TMS treatment, that's where the X value increased by 1 unit. Then the odds ratio will become E to beta 1. So E to 0.8184. That's why we get 2.27, right? And that's exactly the same as how we calculated by hand from the previous slide, right? That's for sure. So the model does confirm with the actual odds ratio. And also we can do a chi-square test. Remember, chi-square test is the null hypothesis is there's no relationship between column variable and row variable. There's no relationship. For row and column factor, meaning they are independent. Each one is that relationship. So we run the chi-square test using the R. So basically come up with this, right? So this is data table. We can use the code to put into the RStudio, get this, and then we run the chi-square test using the above data table. And then the data table shows x squared, where chi-square is 6.8168, and the probability is very, very small. This is less than alpha. Alpha usually we're using 0.05, right? So meaning reject HO. That means there's a relationship between the row factor and the column factor, right? Meaning the treatment does have impact on the pain relief. And also we run a binary logistic regression model, then we just confirm that is a significant predictor, right? So the two tests, the chi-square test that confirmed with the binary logistic regression. Significant predictor. Okay. So that's basically another way of looking at this outcomes, right? So response variable is Y variable. So we have success of failure. Prediction variable is group 1, which is TMS, right, over probability of TNFs over probability of a placebo. Method 1 is using binary logistic regression. Method 2 using chi-square test. And two tests does give us, both tests give us the same result. Right? They are equally effective in terms of assessing the effectiveness of the predictor variable. And then let's go back to the golf carts data. Okay, let's calculate the odds ratio for each one of these from different length, right? So for the 5 feet length, odds ratio is going to be 0.5648, and then this number 0.5648 basically is coming from 61 over 108, right? So you do this is equal simply as 61 over 108, and basically we get 0.5648. That's probability of success, probability of made parts over probability of missed parts. Okay, so 61 over 47, that is odds ratio for 5 feet. And then odds ratio for 6 feet, very similar, using similar for 6 feet, using 61 over 64, right? So it's 0.953. And if you want to do a 3 feet, no problem, you can do that. 3 feet, the odds ratio is going to be 84 over 17. 84 over 17. If you put in the calculator, let's see what that is. Well, you can compute it using any Excel or any software you want to use. You get 4.94. And that matches with all these numbers. You can see, and let's say for 7 feet, the odds ratio is going to be 44 to 90, and that is 0.49. So let's learn how to interpret this, right? So odds using data for 6 feet, odds using data for 5 feet, and if you do the quotient of those two, you get 0.73. Odds ratio of 6 feet to 5 feet, that's 0.73. So that means the odds of making a part from 6 feet are 73% of the odds of making a part from 5 feet. Meaning it's less likely, right? 73% of less likely to making a part at 6 feet. Yeah, so basically from there we can do the odds ratio for any two of them, right? So divide this one is calculated using 2.839 over 4.941. So we get this odds ratio from 4 feet over odds ratio from 3 feet. And similarly, second one, you do 1.298 over 2.839, we get this 0.457, and that's the odds ratio of making parts at 5 feet to 4 feet. Same thing, right? The next one is 0.953 over 1.298. This 0.734. And the last one is 0.489 over 0.953. So odds ratio is 0.513. So I'm basically using this logistic regression in terms of interpreting the slope using the odds ratio. So when we increase the x value by 1 unit, right, the ratio of the new odds to the old odds is e to the beta 1. That's exactly the essence of this slope, right? So this represents slope. And then let's take a look at the odds ratio for plots from samples from the sample data. We get different odds ratios. And if you're using the fitted logistic regression model, you get a constant odds ratio. Right? It's the same. Has to be the same, right? It'll be e to the beta 1, right? Always going to be e to beta 1. And in the logistic regression model, odds ratio will remain constant when increasing the predicted variable by 1 unit, meaning going from 4 feet to 3 feet, 3 feet to 4 feet, 4 feet to 5 feet, 5 feet to 6 feet, 6 feet to 7 feet. And this is the code for the logistic regression. Also, we start with the ANOVA, right? And then for the ANOVA test, the null hypothesis issue is there's no difference for the row factor and the column. There's no difference among group means. There's no difference in the H1H. There's a difference among group means. That is difference. In this case, if you look at the summary output, as you can see, we get a residual difference, and here the degree of freedom. Then we come up with this output that so the ANOVA output does confirm with the logistic regression model, right? That's what this means. And then our logistic regression model is going to be LN log of pi over pi. This is beta 0, beta 1. As you can see, the p-value is very small, so length is very significant, very significant predictor. So it also confirmed with the ANOVA output, right? In the ANOVA output, we reject HO, and that means there's a real difference between amount of group means. That means TMS, average for TMS to reduce the pain versus average of placebo to reduce the pain are different. So it's 3.25684 minus 0.56614 times length of plots, right? So that gives us the logistic regression model. And this is the code to understand the data structure, FTM data structure. We run a logistic regression model using this. We generate a model from earlier slide. Yeah. And this is one of the real world examples, right? From the 2012 election, presidential election. In 2012, Democrats had a decent chance, even if Obama got only 50% vote in district. So if you look at any like 50% right here. So as you can see, with the 50% of the voting in the district, in 2012, black line is 2012, and green line here is 2014. And the chances of voting for the Democrat is higher than the chances of voting for the Democrat in 2014, right? 2012 is about 50%, and in 2014, it go down to 30%. So that's a highly, in 2014, that was less likely for the Democrat to vote in the district. Yeah, so again, we're working on a binary logistic regression model with one predictor variable, single predictor variable. And this is the logistic regression model and the probability form. We've been talking about this extensively. Now let's look at with multiple, right? If I say there's a multiple predictors, in this case, logistic regression model will look like this: beta 0 plus beta 1x1 plus beta 2x2, all the way up to beta k xk, right? So in here we have a k different predictors, k predictors variables. And so the probability form, going back to the transformation, so as a probability of a success or proportion of success equal to e beta 0 plus beta 1 x1 plus beta 2 x2 plus all the way to beta k xk over 1 plus e beta 1 beta 0 plus beta 1 x1 plus beta 2 x2 all the way to beta k xk. That's how we go from the logistic regression model to the probability form. And this is one of the examples. Interaction in logistic regression. Consider survival in ICU as a function of the systolic blood pressure. And we're using this abbreviation BP. Right? BP is systolic blood pressure for short. And the sex. So we run this model, logistic regression model, with the interaction factor, right? BP times systolic blood pressure interact with the sex. And we come up with the following models here. So the way how we write the model will be log. So we log pi over 1 minus pi equal to, this is beta 0, beta 1, beta 2, beta 3. So it's going to be e2 minus 1.439304 plus 0.022994 plus 1.455166. Oh, this is times BP, right? First predictor is BP, second predictor is sex, third predictor is BP interact sex. So this one is plus minus 0.013020 times BP interact sex. And that's how we write a logistic regression model. And we can also calculate the pi from there, right? It's going to be E minus 1.439304 plus 0.022994 times blood pressure plus 1.455166 times sex plus minus 0.01320 times the interaction of the BP and sacks. On the bottom is going to be 1 plus E to minus 1.439304 plus 0.022 divided by 4. That's okay. With a different color. It's minus 1.439304 plus 0.02294 times blood pressure plus 1.455166 times sex plus minus 0.01320 times interaction of the BP and sex. So that's basically how we generate a model from the our outputs. I hope this will help you, get better understanding of logistic regression